All right, and welcome to video 4 of 5 for the central limit theorem. There's been a lot of theory, but now we're just going to work some problems. And one thing I wanted, this should tie it all together for you. We've kind of digested a lot here, but now when working these problems, I want you to remember one thing, is that if you feel good about working the problems that we've done in the past, that we did today in class, that we did on the boards around the sides, and all the normal probabilities where we find the z-score, look it up in the table. If it's an upper tail, we're going to subtract it from 1. If you feel good about drawing and shading, finding the z-score, and then finding the probability, the only thing that's going to change here is that when you find the z-score, you're not going to divide by sigma, you're going to divide by sigma over the square root of n. It's the only difference. Instead of using sigma, you're going to use sigma over the square root of n. So what we're going to do here is I'm actually going to do a sample problem, one in which we just do what we've always been doing and just find the normal probability, and then we're going to find the probability of an average being above or below some number. So you're going to see more of what I'm talking about here. Just remember, the only difference in this whole thing is instead of using sigma, use sigma over the square root of n. So here we go. So here is the problem. Notice that scores for men on the verbal portion of the SAT test are normally distributed with a mean of 509 and a standard deviation of 112. Randomly selected men are given the Columbia Review course before taking the t-test or before taking the SAT test. So what we want to do here is ask a question. So here comes the question. If one of the men is randomly selected, find the probability that his score is at least 590. So really pretend you're in this problem. We've got this population with a mean 509 that are normally distributed, huge, right? We can use the table automatically. And it has a standard deviation of 112. Now we can find z-scores. If you know the mean and the standard deviation, you know a lot. So what we're going to do now is just simply select somebody from that population. Of course, we think they'll probably be close to 509, but what is the probability they'll have this big score bigger than 590? So let's go ahead and come over here real quick. Come on over to the board, and we're going to do this problem. It's the same way that you've been working problems the whole time. So I just kind of want to remind us of where we came from. The only difference when we move on from this is that instead of using a z-score, I'll put it right here. Instead of using z equals x minus mu divided by sigma, we're going to do another problem here in a minute. That's going to become sigma over the square root of n. That's going to be the only difference. But this one should feel nice and like home. So what we want to do is first draw and shade. I'm going to draw the distribution. We know that it has a mean of 509. And what we want to do is say, hey, what's the probability of being bigger than 590? The probability of being bigger than 590. The probability of randomly selecting somebody, some test taker, and his score or her score being bigger than 590. So what we want to do is first draw and shade. Second, find the z-score. And here comes the z-score. We know that z equals 590 minus mu, which is 509, divided by sigma. Notice this is just of the individual, sigma x, which is 112. This is what we've been doing for the last week. And this is, if you do this math, that turns out to be a grand total of 0.72. That's a z-score of 0.72. So what we're going to end up doing here is this is 0.72. And that's all. So I want probability that x is greater than 590 is equal to the probability that z is greater than 0.72, all stuff we've done before, which we know is 1 minus the probability that z is less than 0.72. Got to put my z in there. Don't leave out the z. We got to say what's in there. So the probability that z is less than 0.72. And what is that? That's equal to 1 minus the probability, if you look this up in the table, which is why we change it to a z-score so we can use the table, is 0.7642, 0.7642, and that becomes a probability that we're looking for. It looks like 0.2358, 0.2358. And if we left that as a percent, that's 23.58%. So what is the probability if we randomly select somebody from this population, from this test taker's population, we would get somebody who had a score bigger than 590. and it's actually 23.58% chance. So that's pretty big percent chance. But notice that that was of the individuals. Now we want to ask a different question, right? So we'll go back to the board. Got it. So we go back to the big board over here, and that is, our board is turned off, but no problem. We're going to turn it back on. Not sure why it went off. So that's okay. Bring it back over here. We've had that problem before. Come on back over. This is just like being in class. So I'm going to go off the screen here. Maybe we can show the screen. Can the screen be shown? We'll go over here to the screen. So the screen, this is the second question. So if 16, we're here now, if 16 of the men are randomly selected, find the probability that their average, and this is what you're going to be looking for on an exam. Here is one, find the probability that his score, this is the average score, is at least 590. Think about what that means. It's probably pretty hard to find 16 people and have their average score be bigger than 590. That would have to randomly get a bunch of people with high scores. And given this distribution, it may not be likely. But let's go ahead, bring it over here, and we're going to do this problem. So, now we're asking about mu x bar. But we know mu x bar is equal to mu x, which again is equal to 509. And I would encourage you to just get this out of the way in the beginning. So sigma x bar, because we're asking about the distribution of averages of size 16. This is like rolling the dice 16 times and taking the average, except we're pulling 16 test takers and taking their average score. And we want to know the distribution of that so we can find the probability that that happens. So coming back over here, this is sigma x bar equals sigma x over the square root of n. And let's find out what that is. Ba-ba-ba-bum. So there we go. This is 112 divided by the square root of n, which in our case for this problem is 16. In this case, in our problem, is 16, right? We'll just put that over here. N equals 16. We're taking 16 test takers. So that's it. And if you actually do this math, we have, this equals to, looks like 28. It's 112 divided by 4, which is equal to 28. So, okay, so if we want to do that, then we've got everything we need here. So now I'm going to draw and shade. I'm going to draw this distribution. Notice this distribution, one more time, sorry to go back and forth, is the normal distribution with 509, but its standard deviation is 112. This distribution over here has a standard deviation of 28.
Light over there.
What's that?
Light.
Oh, light?
Yes.
Oh,
And one more.
hello. One more?
Yeah.
Thank you.
You're welcome.
Thank
Thanks a
you.
lot. Awesome. Oh, thank you, but we have to turn them off. So great. But that was very nice. That was awesome. Okay, notice this standard deviation is 28. That one is 28. The other one was 112. This one must be so much narrower, but it still has the same mean. But notice this standard deviation of the x bars is only 28, where again the other one was 112. So we can be more accurate. We think these x bars should be close to 509, which means if you think about it, just think about what kind of makes sense, is that to get an average now, a big average, we're going to have to pull from, we'll come back over here. If I want an average bigger than 509, that means most of the pulls are going to have to come from these people with big test taking skills, with big test scores over here. Where I'm more likely to sample from here to get a mean bigger than 590, they're going to have to come from over here. So that's why when we look at 509, or keep doing that, for 590, if I look at 590, that distribution, now look how much smaller that area is. Look how much smaller that area is. It's much smaller than this one over here. But let's actually calculate what that is. So this is the difference. This is using the essential limit theorem. Notice what I'm going to put. This is the probability that the average, not an individual, but if I pull 16 people from over there, their average is bigger than 590. And let's just plug and chug. So this is equal to the probability that z, we want to translate that into a z-score, is bigger than what? So I'm going to do that right here. That's z equals, right? That z equals x bar minus mu divided by, and this was the difference, right? Sigma x divided by the square root of n. That's the only difference in the whole equation. You get that guy right there, then we're good. And that's what we've calculated. So z now equals x bar, right, which is our 590, minus mu, which is 509, divided by, and we already did it, right? Sigma x bar, which is sigma x divided by square root of n. We did all that, it's equal to 28. And if you do the math on that, that will be equal to a whopping 2.89. That will be equal to 2.89. Excuse me. So that'll be equal to 2.89. So this is, I'm going to move this around just a little bit. This is equal to the probability that z is greater than 2.89, which notice if I plot that on my z chart over here, on my z, this is 2.89. So far I've drawn in shade, I've found my z-score. In order to do that, all I had to do is not divide by sigma x, but by sigma x over the square root of n. And that'll be the probability of x bar is greater than 590 equals the probability that z is greater than 2.89. This is just like the rest. So I'm saying this is just like the other problems that you've done. So now this is 1 minus the probability that z is less than 2.89, which is equal to, if you do the table lookup, that's equal to approximately 0.9981. 0.9981, and that's going to be equal to 0.0019. What a difference. Remember in the last problem that was 23% of pulling one person, but if you want to get an average of 16 people, it's harder to get the average to the extremes. 0.19%, 0.19% chance. That is your first look, and that's the only difference. If we pull it up here one more time, this, I'm going to highlight it with some red. This guy is the only thing that changes in this section. There's some big ideas out here, but it's sigma x over the square root of n. You're just going to, instead of dividing by sigma x, you're going to divide by that, and you will have it. So I've decided we're actually going to stop on this one, and actually let's not stop. Oh, we got to stop. Shoot, because the PowerPoint went out. So we're going to fix the PowerPoint. We've got to have 6 videos, but this one's a little shorter, so see you back in a minute. Central limit theorem. Nice work. Whammo. Boop.